When two ocean plates collide at a convergent margin, one is going to buckle upward and one is going to cave or slide underneath the other. This is similar to what happens in an ocean-continent collision, but in this case, the volcanoes are going to be coming up directly from the seafloor. Some of these volcanoes can be quite substantial, and here we have a Aleutian example of an island arc. These are the Aleutian Islands of Alaska that stretch from North America over here to the Asian plate over here, just to the east of Kamchatka. And these volcanic island arcs are very common around the world. So we can see another one here, Kamchatka, down to the Japanese islands here. And if we were to continue on further south, we'd see the Philippine Island Arc, the Marianas Island Arc, and so on. Now, the reason these are arc-shaped has to do with the Earth being a sphere. It's really difficult to explain in a two-dimensional fashion here. You really need a three-dimensional object to do this. Although I did see it done once with a shoebox and some pieces of paper in kind of an interesting way, but I forget how that's done. Now, if we have a collision between two continental plates, we get a different outcome. Whereas with the ocean plates colliding, we have one slightly weaker plate giving in and sliding beneath the other. Here, in the case of continent-continent collision, both of the continents, being really buoyant, are going to refuse to give in. They're going to refuse to be forced underneath one another. So it's like an ongoing pileup in an icy fog on a highway. Cars keep sliding in from behind, making the pile bigger and bigger. The same thing is going on here with these two continental plates. They continue to press together. As they press together, they're going to be forced upward because they're buoyant. Now, one of our best examples, if not the best example, is the compression that occurred when the Indian subcontinent crashed into Asia. And the result being the Himalayas popping up along with the Tibetan Plateau has an altitude of around 20,000 feet, and the Himalayas get up to substantially higher, with Mount Everest pictured here being the highest point on the Earth's surface. So here we have a cartoon that illustrates what's happening. In this cartoon, we have the Indian-Australian plate coming up from the southwest, crashing into the Asian plate here. And upon crashing into this plate, the Indian-Australian plate is going to refuse to be subducted. So it's going to bunch or stack up slices and slabs and blocks of this material, ultimately resulting in the Tibetan Plateau. I mentioned earlier in the class that this is a bit like a margarita or any other slushy drink you prefer, in that there are chunks of rocks here sitting in kind of a weird slush. And this gives the Tibetan Plateau its extreme thickness of about 200 kilometers. Now, what we get as a result of this collision is this crustal thickening. We get extremely contorted, folded mountains, and we have lots and lots of earthquakes. Essentially, wherever you see mountains, there were earthquakes that made those mountains, and in most cases there are some earthquakes continuing to this day. The more rugged the mountains look, the younger the mountains are for the most part. Now, there was a time 1 billion years ago or so that northern Saskatchewan would have looked something like this. Some very high mountains that have subsequently been worn down to pretty close to flat. This brings us to our last type of margin, a transform margin. In this case, there's no creation or destruction of plates. The plates merely slide past each other, grind or slide past each other. And there's some deformation right along that boundary, but it's mostly ground up rock. So we pulverize some rock right along the fault. Other than that, there's very little distortion to the plates. Here we have a transform fault boundary. In this case, the continent of North America to the west. We're going to take a look at these things in the real world now. Here we have the Pacific plate, which underlies the Pacific Ocean, the eastern Pacific Ocean anyway, sliding past the North American plate. Now, this is an exhumed portion of the plate, so it's sticking up above sea level where it's sliding past the North American plate. So we're going to look at a lateral transform fault and we're going to look at some earthquakes that occur along this transform fault. Very famous fault, if not the most famous fault in the world, known as the San Andreas Fault. It's not the biggest fault, it's not the baddest fault, but it's the most famous fault. It happens to run through two very large cities, San Francisco here, Oakland, which is considered sort of the same city, we're right there, and then the other big city would be LA down here, Los Angeles. It runs through some prime real estate here in the western US, and that's one of the reasons it's famous. A couple other plates here to consider. We have the Pacific Plate, which is sliding to the north, relative to the North American Plate, which comparatively is sliding to the south, although in reality, which one is doing the most moving doesn't matter. So here we have a view from Joshua Tree, which is located in New Mexico and California. Here we have the valley, Coachella Valley. This is where the music festival occurs, somewhere around here. This is a typically very hot day. I think it was 47 degrees centigrade on this particular day. The area is having bee problems, apparently, aggressive bees. This is great when you're motorcycling through in extreme heat and you see warnings to stay in your vehicle with your windows rolled up. Don't get out of your vehicle. Don't leave the air conditioning. Keep your drinks inside your vehicle. If bees threaten you, seek shelter in a closed vehicle. You don't have any of these things. If you're being stung, don't react. Easier said than done. So looking at the Coachella Valley here, we have the Pacific Plate located off here in the distance. This is moving in this direction very slowly, but very more or less steadily. And the North American Plate comparatively moving in this direction. So North American Plate here, Pacific Plate here. Pacific Plate moving this direction, North American Plate moving this direction, right underneath all these Coachella music fans. Just to summarize the three types of plate boundaries, we'll start out with the Rift Valley. We saw the example from Thingvellir in Iceland and from the East African Rift in East Africa, where a continent is peeling apart in the case of Africa and a mid-ocean ridge is rifting apart in the case of Iceland. Complicating things in a slightly different way, we have the collision of two ocean plates here, where we have the formation of a trench. So one plate is being subsumed, it's sliding beneath another. This plate boundary is going to generate significant earthquakes. That's going to be dependent upon the rate of movement of the plates and the depth of the earthquake itself. The result of the subduction, decompression, melting here that we can see resulting in volcanoes. So we have a volcanic island arc associated with this trench, which is in turn associated with one plate being subducted underneath another. And then our final example here is a transform plate boundary. The North American Plate here, Pacific Plate here, sliding past each other and generating the earthquakes that make California famous. The Loma Prieta that we saw in the last video, and of course the Great Quake of 1906, I think April 14th, 1906, that destroyed San Francisco. So those occur on this transform boundary here. And just looking down from above, here we have the East African Rift. So Africa is essentially splitting apart. It's been trying to do this for a very, very long time, at least 20, 30 million years that I'm aware of. So it's not working out yet. The Red Sea is also a rift basin. So we have rifting here. We have rifting down through East Africa, separating Ethiopia from Central Africa here. Sorry about the barking. But nonetheless, there's a split here, or an attempted split of the continent. In the case of the mid-ocean ridge in the Atlantic, here we have some color images of what are known as black smokers. This is very high temperature water coming out, heavily laden with dissolved ions. And as this water goes from 400 degrees centigrade to 2, it rapidly precipitates these minerals. Anoxic plume water to oxygenated water here. And that also aids in the precipitation of these very fine-grained minerals. And we get an abundance of sea life associated with these chemical reactions, which essentially what these things are, these hydrothermal vents. If we plot this information up, if we plot up earthquakes relative to their depth, the depth of the focus, we see some features that look very coincident with faulting features. So this adds up. This makes sense. The earthquakes are occurring where we see faulting, and the depth of those earthquakes is going to be dependent again on what's being subducted and how fast it's being subducted. If we strip away the earthquake information, we can more clearly see these arcs, arcuate features here. So the Aleutian Island arc here, Japanese Island arc here, the Philippines here, Marianas Islands here, Puerto Rican Trench over here, Scotia Trench here, and so on. Again, these arcs, like Indonesia here, are created because the Earth is a sphere, and it just works out geographically that these would appear to be arcs on the surface based on what's going on beneath the surface. So here's a cartoon of a lot of that plate activity kind of combined into one unifying cartoon. We have a continental plate here, say North America, looking from the north to the south. We have a passive margin, no tectonic activity along the east coast of the United States, for instance. We have the abyssal plain leading out to the Mid-Atlantic Ridge, and at the Mid-Atlantic Ridge, along the axis, there's spreading. Plates are diverging, they're moving apart this way and this way. Eventually, this plate is going to reach another plate. In this case, can't tell if this is continental. It looks like continental crust here. And this oceanic crust is going to slide beneath this continental crust in this case and generate some intermediate volcanics. So andesitic rocks, kind of a grayish color in general, is the rock that would result from this kind of tectonic activity. There are a couple different models for how the mantle is moving. One is a multi-cell model where we have upper cell convection, and lower cell convection. So in this case, the upper cell convecting in this manner, the lower cell in this manner, working its way all the way to the core mantle boundary. Alternatively, we have evidence for whole mantle convection, where the entire mantle can be one giant convection cell. So again, there's evidence for both of these, and whether we really need one to explain everything or not, yeah, that's a whole other argument. The lumper splitter argument, and common in many sciences. What's driving all this? Well, it turns out we don't know. The ideas are ridge push. So ridge is being created here along this axis, and the creation of this material is going to push adjacent material away. Alternatively, we have mantle drag. So we have convection in the mantle, like so, grabbing onto this plate and dragging it. Because this plate is dragging away from its hot source, the originator source here, it's cooling off, it's becoming more dense. As it becomes more dense, it wants to descend into the less dense surrounding material. So we have the mantle dragging this material that's getting cooler and denser downward. And eventually it's going to heat up again. And if it heats up sufficiently, it'll generate magma and result in volcanics. But if that doesn't happen, this slab can go all the way down, potentially to the core mantle boundary, and pile up in that slab graveyard that we all fear this time of year. There's a trench that's going to be created. It's thought that trench suction may play a role in what's happening here, where material is being driven down from the lithosphere into potentially the asthenosphere or even the upper mantle. Now, when we put continents back together again, we reconstruct them based on the age of slabs, slices, and blocks. We can see that accretion for North America depicted here, where we have some of the oldest rock up in the northern portions of Canada, in particular in the Northwest Territories. I started grad school at Washington University in St. Louis, and one of the professors was working in this region with a whole bunch of his graduate students. He had nine or 11 grad students at the time. So they were all running around in the woods up here. And at one point, they collected a rock that sat under his desk for years, used it as a footrest. Eventually, he determined the age of that rock, and it was the oldest rock ever discovered on the surface of the earth. So that was something. And again, it was a footrest for a couple of years. So that was found right around here. Subsequently, some older minerals have been found in Australia, but the oldest rock, to my knowledge, is still a gneiss that was recovered from around here. Canada has this continental core or interior, and South America has a similar one. Africa, Asia, all of the continents have these types of original cores that over the years, over billions of years in this case, other material gets slapped onto and accreted to, forming the continental outlines that we observe today, ultimately. What all this means is that plate tectonics drives the rock cycle. Almost everything we see on the surface of the earth today is a result, one way or another, of plate tectonics. So we'll start out with some igneous rock being formed from a volcano. That igneous rock is going to be weathered, and it can be weathered and eroded and material moved away, becoming sediment. If it's solid material, if it's dissolved material, it goes into the oceans where it may spend a considerable amount of time before it becomes rock again. If it's clastic material, chunks, then it can be deposited and lithified, made into sedimentary rocks, which can be uplifted and re-eroded and become new sediment, or it can be heated up and combined with fluids and turn into metamorphic rock. This metamorphic rock can in turn be uplifted, weathered, eroded, turned into sediment, and so on, converted back into metamorphic rock. Or it can be driven down into a subduction zone where it's melted. If it melts, it becomes igneous rock. If it doesn't quite melt, it's a metamorphic rock and go back this way, and so on and so forth to the end of time, the beginning of time to the end of time. In general, the drive has been from dark colored to lighter colored through time. The original rocks, komatiites, that formed very, very early in the Earth's history were very, very dark rocks, black igneous rocks. Subsequently, after many, many cycles, erosion, reprecipitation, melting, cooling, erosion, etc., rocks are becoming lighter and lighter in color as we move into the continental interiors of each continent. So we started out with continental drift, an idea by Alfred Wegener. This was, it turns out, a really good idea with an unfortunate name. The fact that he called it continental drift was its undoing. So geologists jumped in and said, this guy is a European mathematical meteorologist kind of guy, so he doesn't know what he's talking about. How can the continents drift? How can continents float? Why would rock float? And if it is floating, why would it move? And Wegener didn't have a mechanism for that movement. So started out with a good idea. The bad people came after him, the know-it-all geologists, and they ruined his life. They tried to ruin his career. He remains famous to this day for his work in Greenland and on the jet stream and that kind of stuff. He has a really interesting personal life. One of his buddies was Milutin Milankovitch, who's responsible for Milankovitch orbital forcing of climate, which we're going to talk about later on in this course. He married a woman whose father was Vladimir Kopin, of the Köppen climate classification system. He was basically Mr. Earth System Science 100 years ago. Knew the right people, he lived in the right place, did the right thing, and the bad people came after him and wrecked his life. So ultimately, he continued on with his Greenland research until his untimely death, most likely from smoking and a heart attack on a Greenland expedition in 1930. By the 1960s, Harry Hess and other U.S. naval individuals looking at the data that was gathered from World War II started to reconsider Wegener's ideas, and they put it together as the theory of plate tectonics. And that's the idea that stuck, and that's what we talk about to this day. One of the most important critical geologic theories that we have is plate tectonics, and it's very new. It has come about during my lifetime, which might seem like a long time to you guys, but for me, it's not that long yet. Anyway, so we'll leave it there, and we're going to move on to carbon cycling next.